In recent years, one telescope has captured the imagination of the entire world, the James Webb Space Telescope. Even if you've never searched for it, you've probably heard people talking about it. It is more powerful than any other space telescope, including Hubble. So big, it had to be folded up like origami to fit onto the rocket that carried it into space. So precise and sensitive, it has to be kept at temperatures not much warmer than absolute zero to prevent its own internal heat radiation from getting in the way of its sensors. So expensive, it cost $10 billion to make, and so complicated, it took decades to complete. 300 potential failure points stood between it and proper functionality. But now, it has been operating successfully for several years, and it has an incredible mission: to study planetary systems for evidence of life, to understand the formation of planets, stars, and galaxies, and to peer out across the universe to objects so far away that the light they gave off has been traveling for almost as long as the universe is believed to have existed. In other words, the JWST was built to spot the first stars and galaxies at the very edge of our knowable universe, objects from the beginning of time. It was first conceived in the 1990s and was originally intended to cost only $1 billion and launch in 2007. However, numerous setbacks and delays plagued the project, pushing it back again and again. It was only in December 2021 that it finally launched, and over the following months, it slowly unpacked itself, powered up its systems, and tested its hardware. It is a 6,500 kilogram monster with a sun shield whose 14 by 21 meter dimensions are around the size of a tennis court. Its mirror for capturing light is 6 times larger by area than Hubble's mirror, which allows it to pick up more photons from farther away to create crisp images. It boasts numerous cameras and scientific instruments, which allow it to see across the infrared spectrum. This is a feature that is vital to its unique mission. Due to the expansion of the universe, all of the light from the furthest reaches of space has been stretched to the point that, no matter what they were to start with, they are all at least infrared light now. So the only way to see these light sources is with an infrared telescope. On top of that, infrared is better at punching through dust clouds and other obscuring debris, giving the James Webb Space Telescope the incredible ability to see objects that are beyond the sight of Hubble. I compare this telescope with Hubble a lot, as the James Webb Space Telescope was originally intended to be Hubble's successor. However, given their slightly different fields of view, Hubble can mostly see invisible light spectra, while the James Webb Space Telescope can almost exclusively see infrared and can't see some visible light wavelengths at all. It's more accurate to say that the two telescopes complement each other rather than compete. They work together to form a powerful duo, expanding our understanding of the universe. But that's not what you're here for. You are here to see what James Webb can do. Beginning in our own galaxy, let's gradually expand our vision outwards toward the edge of the knowable universe. You are in for some spectacular sights. The first stop on our journey is a place known as the Cosmic Cliffs. The Cosmic Cliffs, otherwise known as NGC 3324, are a part of the Carina Nebula, about 7,600 light-years away from us. These peaks you're looking at are massive structures around 7 light-years high, and what you see here is only a portion of the nebula as a whole. The actual nebula is much larger and contains a hollowed-out center where the stellar winds given off by stars have blasted all nearby dust away from them. What we're looking at here is the edge of this hollowed-out bubble. Scientists are very interested in this region of space for one very simple reason. It helps answer questions about the formation of stars. Thanks to the stellar winds in this zone, dust and matter conglomerate together, forming a birthing place for stars. However, for all our stargazing, there are still many mysteries surrounding this process. How exactly do they form? What do the different stages look like? It's difficult to tell. Part of the difficulty with finding the answers is the dust itself, both vital to the process and also a massive impediment to seeing it happen. It wraps around the forming stars like a protective cocoon, stopping scientists from seeing very clearly what is going on at the moments we'd like to see the most. James Webb fixes that. Not only does this image provide more detail than Hubble's image, but thanks to JWST's onboard MIRI, or mid-infrared instrument, we can peel back the layers of dust and see what lies within. See how much clearer the image is. This will provide scientists with data on the formation of stars for a long time yet. So much for the birth of stars. At our next stop, the JWST uncovers more about the end of their lifespan. For this, let's look a little closer to home at NGC 3132, otherwise known as the Southern Ring Nebula. The image on the left was taken by JWST's near-infrared camera, NIR-CAM, while the one on the right was taken by MIRI. This is a planetary nebula, although technically that term is a bit of a misnomer. While regular nebulas are birthplaces of stars, a planetary nebula is not a place where planets form. Instead, it was just an unhelpful neighbouring convention used by early astronomers who noted the round shapes of these nebulas and thought they looked a bit like planets. The name stuck, even though our interpretation of the name has moved on. Planetary nebulas like this one are formed when dust and gas are blasted out from dying stars towards the end of their lifetimes. Knowing the chemical composition of this dust is useful, as understanding what materials exist in the universe helps us to understand what later waves of stars might be made of. So, once again, James Webb's ability to peel back the layers of dust and see what lies within is invaluable. Compare this with Hubble's image to get a sense of the increased detail that JWST is able to bring to bear. From this, scientists learned that the second star within this system had not actually exploded, so the formation of its own planetary nebula was likely still to come. We can also get a better sense of how the gravitational interactions of the two stars stir the nebula, mixing the dust together in fascinating patterns. Now, let's look a little farther out, beyond our galaxy. If we want to see star creation, it makes sense to find a location like this. 161,000 light-years away from us lies the Tarantula Nebula, so named because it evokes the idea of a giant tarantula lurking within its silken web. Aside from its obvious otherworldly beauty, this area is of particular note to scientists because of its similarity to a period in the universe's history known as the Cosmic Noon. At that point, which, to our best understanding, took place about 1 billion years after the universe began, star creation was at its most prolific. It is thought that conditions there would have looked something like this. James Webb has identified stars here that are only just coming into being, a fascinating period of time to study. Let's look farther out again. As our gaze extends, we lose track of individual stars and start seeing things on a galactic scale. Even here, there are beautiful dances being played out. Stephan's quintet is a formation of 5 galaxies, although one is not really next to the others, but just looks that way from our perspective. Famous for being featured in the film It's a Wonderful Life. It is thought that 4 of these galaxies will one day collide. Indeed, 2 are already doing so. James Webb allows us to see clearly the brilliantly hot dust being kicked off as these 2 central galaxies circle each other. The gravitational forces here are mind-bogglingly intense. The energy is profound. It is a dance that is truly only appreciable at scales like this one. This image was not taken at a single time, but is actually a composition of almost 1,000 separate images that James Webb took and that scientists then put together, giving it incredible resolution for picking out details. Let's look farther out again. Until even James Webb is straining to see. In an image known as Webb's first deep field, James Webb peers farther into space than ever before. This image is taken from an area so small that a single grain of sand held out at arm's length would block it from your view in the night sky. At this scale, individual stars are almost completely absent. Most of what you see here are not stars, which would be too small to detect on their own, but galaxies. Here you can see the lensing effects being created by gravitational warping, as relatively nearer objects bend light around them, distorting what lies beyond. We can start to see the edges of the universe. In this image is one of the oldest galaxies we have ever sighted. It is so far away that the light from when it was born at the beginning of the universe has only just reached us. Where is it? We are going to need to zoom in. Do you see it? It is admittedly quite small. By evaluating markers within the light given off by this tiny red galaxy, scientists are able to identify how far it has redshifted, and thus how long the light from it has been travelling, by comparing it to normal visible light from similar sources. This tiny dot was found to be 13.1 billion light-years away. As far as we know, given that the universe is thought to be 13.7 billion years old, this is one of the earliest galaxies we will ever be able to see. Now, you might be disappointed by how small it is. However, there is some room for hope. Compare this image with a similar one taken by Hubble of the same region. Obviously, JWST's image is crisper and clearer, giving more detail and showing more objects. But there is one other vital distinction between these two images. Hubble took its image by staring at this patch of sky for 10 days, slowly gathering every photon it could from this region of space and compiling them into a single image. JWST, on the other hand, took only half a day to capture its own image. What this implies is that if JWST was able to take such a detailed image in 1/20th of the time, imagine how detailed an image it could take if given a comparable amount of time. In other words, this tiny little dot is likely not the best that the JWST can do. I hope these images have given you both a sense of the scientific breakthroughs made possible with the JWST, but also just how beautiful the sights in the universe are. Images like these blow me away. Sadly, we are going to have to be a little patient to see what other discoveries the JWST might have in store for us. Since completing its calibration phase, the JWST has been operating at full scientific capacity, with scientists around the world continuing to use it for groundbreaking discoveries. There are queues of scientists fighting over who gets to use it to do what over the next several years of its expected lifespan. Each second is hotly contested. It continues to investigate exoplanets for signs of hospitable atmospheres for life, unveil nebulas to find the origins of stars, and help us understand the difference between an old galaxy like ours and the young galaxies that formed just after the Big Bang. With a tool as powerful as the James Webb Space Telescope, who knows what else we'll discover? Thanks for watching.